Hi, my name's Aubrey Goff. This is my video report for Lab03, Black Hole and Orbits. In this lab, I analyzed the motion of a star near a black hole and simulated a spaceship attempting to orbit both a planet and its moon. So in estimating the black hole's mass, I calculated the net force acting on the star at each point in its trajectory. That was derived from the rate of change of the star's momentum, according to Newton's second law. And after looping through the data and applying this method, I got a series of mass estimates for the black hole and then averaged these values to give me a final estimate of the black hole's mass, which we'll see in just a second. So the net force on the star is equal to the rate of change of momentum, so delta P over delta T, which we observe through changes in the star's velocity. And then we split that into two components, the parallel component and the perpendicular component. So the parallel component corresponds to changes in speed along the direction of the motion, which tells us if the star is speeding up or slowing down. And the perpendicular motion represents a change in direction, which is critical for, in this case, elliptical motion, and it reflects the centripetal force. So while the rate of change of momentum is computed from the velocity data, the net force is from a physical cause, which is what's making the momentum change. So this would be the only force acting is gravity from the black hole. So for part 2, the orbiting moon and planet, I simulated a spaceship starting on the moon and launching into a trajectory that attempted to orbit both the moon and the planet. So I modeled the gravitational force on the moon due to the planet and the gravitational force on the spaceship from the moon and the planet. And then added a component opposite to the moon's motion to put it into a figure 8 pattern. So the velocity gave the ship a trajectory that curved around both bodies and doesn't simply orbit one or the other, which we can see here when we go through. We can see our two separate components, parallel and perpendicular, and when we run the program, we can see what we would expect to see. And as we're closer in range to the black hole, the gravitational force of the black hole does get larger. So if we wanted to predict the full motion of the system, including the black hole, star, planet, moon, and spaceship, our model would need to account for the relationships between the black hole and the star and the planet and the moon and spaceship, and so on and so forth. But the main interactions would depend on the relative masses of each one. So the black hole's gravity dominates the star's motion, and the planet dominates the moon's motion, and the moon and planet together influence the spaceship. So in a full simulation, you'd model all of these, but we can often ignore the weakest forces since they're not as strong and won't play as large of a role. So I demonstrated how to use real motion data to infer gravitational forces and estimate the mass of a black hole, and I explored the multi-body orbital dynamics in a fake planetary system. And here we can see, as we saw in the motion, we see all the previous iterations of mass, and we come to the final average mass of the black hole. Thank you so much.